Hi there, so this is section 3.4 part 2. So in part 1, we were determining the open intervals where a function was increasing or decreasing, and then sketching the graph from that information. So now we're going to continue on. So the points where a function changes from increasing to decreasing or decreasing to increasing are referred to as local extrema. And depending on the text that you're using, local extrema might be referred to as relative extrema. And I'm going to use both terms. You need to be comfortable with both terms. So local extrema, aka relative extrema. Okay, so a local max will occur whenever a graph changes from increasing to decreasing, and a local minimum will occur whenever a graph changes from decreasing to increasing. And so remember, whenever we were finding the values to put on the analysis line in part 1, we were determining where the derivative was equal to 0 for the functions that we were working with, right, where horizontal tangent lines would exist. And there wasn't always a sign change. So we'll talk later on about what it means if the function at that value just maybe goes from increasing and stays increasing, or decreasing and stays decreasing. But if there is a change from increasing to decreasing or decreasing to increasing, it means that a local extrema exist. And local extrema occur at critical values of a function. And critical values are x coordinates. Okay, and critical points are actual points x comma y, where x would be the critical value for the function. And it's important to understand the difference so that you can appropriately answer a question, and you understand what I mean when I refer to a critical value versus a critical point. Okay, so here are our definitions for local max and local minimums, and I just kind of went through what happens when there is a local max or a local min, but here is our written out definition. So f of c is a local maximum if there exists some interval from a to b, an open interval from a to b, that contains c such that f of c is greater than or equal to f of x. So f of c, that value, that output value at x equals to c, the y value at x equals to c, has to be greater than or equal to the other values on the open interval from a to b. And that needs to be true for all values of x on the interval from a to b. Okay, and then we could say that the local maximum occurs at x equals to c. Or you could also describe the location as the actual point, which would be c comma f of c. Okay, so you can describe using the x value or the actual point. F of c is called the local minimum if there exists some open interval from a to b that contains c such that f of c is less than or equal to f of x for all x on that open interval. So that means that if the output value for x equals to c, so the y value at x equals to c, is less than or equal to the other values on that open interval, then f of c is considered to be the local minimum. The local minimum occurs at x equals to c, or again, as a point, that would be c comma f of c. And it's also important to differentiate between like what the actual local maximum or local minimum value is. That's going to be an output value, so Y value, versus describing the location of where a local maximum or local minimum occurs, which you can then use either just the X coordinate or the actual point. Okay, so our theorem of local extrema, this is important. If a function f is continuous on the interval from a to b, the open interval from a to b, and c is in the interval from a to b, and f of c is either a local maximum or a local minimum, then f prime of c is equal to 0, or f prime of c does not exist. So let's look at each of those cases closer and like what they mean. So f prime of c, we'll use red, f prime of c equal to 0, well, that indicates a horizontal tangent line. Okay, so if the derivative of the function evaluated at c is equal to 0, that means that there is a horizontal tangent line at x equals to c. Okay, f prime of c not existing means that there is a vertical tangent line or a sharp corner in the graph, which we have talked about before when the derivative fails to exist because there's potentially infinitely many tangent lines that you could draw. So either a vertical tangent line. An example of a vertical tangent line could be like cube root of x. Let me just sketch that graph for you. Okay, where the vertical tangent line would occur at x equals to 0. Okay, and then the sharp corner where the derivative fails to exist, an example of that could be like absolute value function at x equals to 0. Right, where you could draw, there are infinitely many tangent lines that you could draw. We could think of as no tangent line. At x equals to 0. Right, there's not one single tangent line that we could draw. Okay, so a local maximum or minimum is going to occur at a point where f prime of that x value is equal to 0 or f prime of that value does not exist. And the values where the derivative is equal to 0 or the derivative doesn't exist is referred to as, those are critical values, okay? And the y coordinates that go with those x coordinates, so like f of c, c comma f of c would be the critical points. So the critical values of x are those values c in the domain of f, and c to be a critical value, a value has to be in the domain of the function. If you remember our example, our last example from part 1, our derivative would have been would not have existed at x equals to 0, right? The derivative would have been undefined there. However, 0 wasn't in the domain of the function negative 1 over x. Therefore, 0 was not a critical value, and therefore was not a potential local max or local min. So just a note, local extrema occur only at critical values. However, a critical value does not guarantee a local extremum. So just because a value is a critical value does not mean that it is a local max or a local min. It is just a potential local max or local min. Okay, we use the first derivative test in order to determine where local extrema exist for a function, or if a function has any local extrema. And we were basically already doing the first derivative test in those first few examples, but we were just not identifying the local extrema. So to determine local extrema for a non-constant function f, continuous on the interval from a to b, you want to find the critical values by finding where the derivative is equal to 0 or where the derivative is undefined, right? Where it doesn't exist. So find critical values. Then draw the analysis line, and this is what we were doing before, and you're going to put on the analysis line all of your critical values in order from left to right. Then using test points, you're going to check the sign of the derivative on each side of those critical values. So you're checking to see what the sign of the slope of the tangent line is to the left or to the right of each of those critical values. If the function goes from increasing to decreasing, so positive to negative, then f of c is a local maximum. Right? So the function evaluated at the critical value is a local maximum. If the function goes from decreasing to increasing, or the tangent lines go from being negative sloping to positive sloping, then f of c is a local minimum. If there's no sign change from left to right of the critical value, then f of c is not a local extremum. Okay, so let's first identify critical values. This is a polynomial function, smooth continuous curve, has a domain of all real numbers, so we don't need to worry about a critical value not being part of the domain. We can find the derivative just using power rule. Okay, so 3x squared plus 2x minus 1. And then setting the derivative. So the derivative of a polynomial function is a polynomial function. So there's not going to be anywhere that the derivative is undefined. We just need to find the values that would make it equal to 0. And we can factor. So we get that our critical values are x equals to 1/3 and x equals to -1. So then for part B, to perform our first derivative test, we'll draw the analysis line just like we did before. And we put those values on the analysis line in order. I also like to label them as being critical values, just to separate them from my test values. So for test values, I could use -2, 0, and 1. And I'm plugging those test values into the derivative because I want to know whether the function is increasing or decreasing, right? I want to know what the sign of the slope of the tangent line is to the left and the right of each of those critical values. So f prime of -2 plugging that value into the derivative, that would be, what would that be? 3 times, so 12 minus 4 minus 1. That's going to be a positive value. You don't have to actually find the slope of the tangent line. You just want to know what the sign would be. So increasing to the left of -1. F prime of 0 would be -1. So changes to decreasing. And then F prime of 1 would be 4. So switches again to be increasing. Okay. So stating the intervals where the function is increasing and decreasing. So increasing from -infinity to -1, as well as 1/3 to infinity, and decreasing between -1 and 1/3. Okay, so because at -1, the graph went from increasing to decreasing, that tells us there's a local max. Right, a local maximum. And it'll be helpful for us to know the actual point. So at -1, comma, and we want to know what the y-coordinate is there. So plugging -1 into f of x. So f of, here, I'll do that over here. F of -1 would be, what? That would be -1 plus 1 plus 1 plus 3. So 4. And then the graph goes from decreasing to increasing at x equals to 1/3. So there's a local min at 1/3, comma, and then finding f of 1/3. And I already did this, so just for the sake of time, it's 76 over 27. Which is, which is approximately 2.815, just for graphing purposes. Okay, and our last step is to put all this information together. So I like to graph the points that I actually know. So those would be the actual local max and the local min. Let's see, what do I have this scaled by? This is probably 2. This is 2, 1.5, 1, 0.5, yeah. So that would be 3, okay. So -1, comma 4. And 1/3, and then approximately 2.815. Whoops. Sorry about that. So 1/3 and then 2.815. Say in there. About. And then you can go off of the increasing or decreasing, or the fact that you know a local max, right? It's going to be curving down around that point, and a local min, it has to curve up, which that also then should make sense with where the function is increasing, the intervals where the function is increasing or decreasing. Okay, so that's a rough sketch of the graph here. Okay, and let's look at this next example. So if we want to find the critical values, we want to find f prime. I don't know about you, I don't want to multiply out x minus 1 times itself 3 times. I'm going to use chain rule. It would be times 1, and then that plus 2 goes away. So setting the derivative equal to 0, it's not going to be undefined anywhere again because we're still dealing with another polynomial function. X equals to 1 would be the critical value, only 1 this time. And then applying our first derivative test, I'm going to abbreviate, making the analysis line, choosing test values, and then plugging those values into the derivative. Okay, so f prime of 0 would be positive, so it'll be increasing. And then f prime of 2 it's also going to be positive. So the graph, we know polynomials are smooth continuous functions. There's no points of discontinuity. So that means the graph will be increasing everywhere. Negative infinity to positive infinity. And there won't be any local extrema. Which makes it very difficult to graph. We do know, though, that there's a horizontal tangent line at x equals to 1. So, like, if we find f of 1, that gives us kind of an idea what happens at that point, right? Having a horizontal tangent line. Okay, so at the point 1, 2, there's a horizontal tangent line, and then the graph is increasing to the left and the right. So, and then falling back on your guys' pre-calc knowledge, thinking translations, transformations, parent function here would be x cubed, shifted right up 2, right? That gives you an idea. You guys are familiar with these types of functions. That gives you a little bit of an idea of what this graph should look like, which would be kind of something like that, right? Where there's a little bit of there's a horizontal tangent line just at the point 1, 2. Okay, so now we're just looking at identifying critical values for some more complicated equations. So remember, critical values occur where the derivative is equal to 0 or undefined. Now, this function we know, it's a rational function, does have a domain restriction. X can't be equal to 4. Right? 4 is not in the domain. There's a vertical asymptote there. To find the derivative, I'm going to rewrite this as 4 minus x to the negative first, so I can just use chain rule. And so the derivative is 1 over 4 minus x squared. If we set that equal to 0, there's no real solution. No horizontal tangent lines. Okay. The only value that would make our derivative undefined is 4, but 4 can't be a critical value because it's not in the domain of the function. So I'm going to write a note about that. So at x equals to 4, the derivative is undefined But x equals to 4 is not a critical value because it is not in the domain of the function. No critical values means no local extrema. This function has no local max or min. Therefore, no local extrema. Okay. And if we try and find critical values for y equals x to the 2/3, just using power rule. So 2/3 times x to the negative 1/3 can be written as 2 over 3x to the 1/3 power. And, well, if we set that equation equal to 0, there's no solution. But the derivative would be undefined at 0. Therefore, there is a critical value at x equals to 0, because, again, that's where the derivative's undefined and 0 is in the domain of y equals x to the 2/3. Okay, so that's just looking at identifying critical values for a little bit more complicated. So I gave you an example of a function that didn't actually have any critical values because a function does not have to have any critical values. This function does. But